Hi, welcome back. So for this exercise, let's say that interviewer gives us, or he or she says like, please construct a function that accepts a list or an array, like this. This array is sorted, and you need to return root node to well-constructed binary search tree, right? So cool. Now, because this list is sorted, one way of solving this problem would be just to start at the beginning and say, okay, cool, we have a root node of 1, and we just append 2 to the right because it's bigger number, right? And we could do this until we hit the end, right? And so on. Like, this would be one way of solving this, but the problem is that when we look at time-space complexity for this solution, we could say that for the time it's O of n, right? Because when construct lookup would be O of n, should I say, right? This is bad because if the binary search tree has minimum height, so if it's well constructed, the lookup should be log of n, right? Cool. So we can dismiss this solution and find a better way. Now, because this is sorted array, we should be doing construction, binary search tree construction like this. So we start at the mid value, which is in this case 5, and this would be our root, right? We of course have our low, so this is low and this is high index. And once we find our root, we just append anything that is returned from the left side. So, and append node dot right should be the node that's returned from a recursive function from the right side, and that's basically it. So let's look at this example going recursively to the left side. We would pass the high pointer like this, right? And we would recurse until low goes over the high. Once this condition is met, we just return none. So in that case, in the last case, node.left would be equal to none, which is what we want. Cool. So what's the time-space complexity for this one? So yeah, for binary search tree construction would be still O of n because we need to look up every node, right? But the lookup would be log of n, like we discussed before. For space, this would also be O of n, and is the number of nodes in a binary search tree. Cool. So I think it's time for coding out the solution. Right. So we're given a list. We need a constructor function, so let's call it construct binary search tree. We pass in a list, and what we expect is to get a root value. Oops, something like this, right? So the next value would be like, let's say 3, 8, and so on, right? Okay, cool. So the first thing we need to do, let's just implement the class node, which we will need this in a bit. So object, we need a constructor, so itself, we need value, left and right node. The right is also none. Right, so we've just constructed node class, which just has a constructor, which will give us our node instance. So now we need to actually construct binary search tree function. We pass it an array. Let's just return helper. This helper, it needs an array, and it needs low and high values, which can start at so index 0, and high will be the last index, which is length of I minus 1. Right? Cool. Let's just implement this helper function. So our base case for this recursive function will be if low is greater than high, we just return none. Because none is implicit, we can remove this. If not, we need to find mid value, right? Which is just low plus so high minus low divided by 2. Right? After this, we need to construct node. We actually need to node because we will be appending left children and right child, right? So it's just node class constructor with mid value like this. And then node.left, it's everything what is returned from recursive function. So we call helper. We pass in. So when we're going to the left, so the low stays the same, but the mid, but the high is mid minus 1, right? For the right, when we're going to the right, the low is mid plus 1, but the high stays the same, like this. Cool. And once we're done with this helper function, we just return node because we need it here. Right? Cool. So just to prove this is working, we will need another function. Let's call it reverse. And we will do it this in order. So once the binary search tree is constructed, the result should be printing 1, 2, all the way through 10, right? So it's easier to see if the constructor function is working. Well, everything is working correctly. So this is the recursive function. We need to start with the base case, this reverse function. So if not node, we just return. We need to do anything. In order traversal, we need to traverse first to the left, then we print, and then we traverse to the right. Right? Let's do that. So node left. In the middle, we just print the node's value. Like this. Cool. So we can traverse this node like this. But before we do this, let's just print the root value, which we expect to be 5, I think. Yeah, 5. So let's run this. Okay, it's 5. So now, if we run the traverse route, we should get the values 1, 2, 3, 4, all the way to 10. And we do get it. So this is working, right? So to recap, how to solve the binary search tree constructor is just to have a construct binary search tree. We choose to have helper recursive function, but we also could do this inside here to have a starter value of 0 and the last index. So this helper function is just a recursive function that is basically doing binary search and constructing nodes, right? And that's all there is. I hope this video helped you in any way. If you like this video, please consider subscribing. Yeah, see you guys next time. Bye.